That one's confusing.
All right, so I passed back your kind of winter break, midterm, take-home test packet, whatever you want to call it, and we'll go over it in a second. But just wanted to let you know because the end of the quarter is coming up next week, I think on Wednesday, okay? So there are very few grades left before that point in time, so we have about a week left. This packet is going to be your last test grade on the quarter, and it's already online, so you can see how that affected or didn't affect your grade, depending on who you are. The quiz that we're going to have on Friday is going to be your last quiz grade for the quarter, and then since it's the end of the quarter, you know you still have the pass-fail to do before Wednesday, or by Wednesday, okay? Now, that grade, if you haven't already passed it, is in as a 0. So your grade technically can only go up from there by at most 5 percentage points. So I know some of you might be on that border, and I think it's the pass-fail that might be able to lift you above that level. Okay, so make sure that you attempt that, try to get it in, or pass it before Wednesday, by Wednesday. Okay. Are there any questions about grades that are left? No. Okay. The video assignment that you have for tonight, 3 pages, okay, 289 to 291. Make sure you comment on the Google form, and this is going to be kind of your last homework grade, I guess, for the quarter, because you do get points for that. Okay, so that's going to be the last one on the quarter as well. When you look through this packet, are there any particular questions or examples that you want to go over? Yeah. 6. 6C. 6C. All right. For a certain value of the constant k, the graph has a point of inflection on the x-axis. Find this value of k. All right, so point of inflection means that the second derivative is 0 based off of our relationships that we've discussed. So from part A, since you had to find the second derivative, I took that and set it equal to 0. Now the problem with this is one equation with 2 variables in it. So you know you're going to have to find, or kind of set up a system, if you will, to help you solve for k, because that's what they want us to do. So I took this information and wrote one equation, and then I took this information and wrote another one. So if you want it to be on the x-axis, you know the original function has a y value of 0. So I took the original function from the top and set that equal to 0. So with these 2 equations, definitely elimination would not work because we can't really stack numbers or variables, so you kind of have to go the substitution route. I solved this one for k, and I actually solved this one for k as well. So if they both equal k, then this fraction and this fraction have to equal each other. And since they both have a square root of x on the in the bottom, we know they already match. So that means the top parts have to equal each other, and that's what I have here. So then I moved the natural log over, changed it to an e. So this is what x is, but they want you to solve for k. So I think I just plugged that in here to get that. Is that okay, Griffin? Mm-hmm. Yeah. Okay. I forget who it was. There were some people that converted this to a decimal, which means that you use the calculator. Okay. I told you could to check, but try to make sure that you can do it without a calculator. So this is what you really should have if you did it by hand. Okay. Are there any other ones you want to check out? 1E.
What's that? Well, when you jump us out, when incorrect this way out. Yeah, I would agree.
1e, you said? Okay, find all values at which f has a point of inflection. This is the graph of a first derivative. So if a point of inflection happens where the second derivative is 0 and changes sign, that would mean the first derivative has to change increasing to decreasing or decreasing to increasing. So those happen at maxes and mins. So -3, 2, and 5.
But at 5, there's... Oh, wait.
5 is a level spot because you're increasing so at 5 you're increasing before level and you're increasing, but this is a point of inflection because you change concavity. Here's concave down and here's concave up. I was surprised, but kind of not, that we had trouble with C. I think a lot of us put an interval from 2 to 5. Is that right? Okay. And you had the right reasoning because f prime is decreasing, but then you immediately stated in part D that the second derivative is undefined at 3 because you have a vertical slope. So there's no way you can be undefined at 3, but also be, there's no way you can be undefined but less than 0 at the same time. Do you see how those are two contradictory things? So if you said 2 to 5 in here, I was hoping that part D would kind of catch you with that because 3 is within there. Christmas, I know. Christmas break. Are there any other ones you guys want to go over? Overall, I think this went really well. The other one that I think some of us just slightly missed was on the back page. Okay, number 10, part B. Almost all of us found that y equals 2 was a spot where you have a horizontal tangent, but for some reason we didn't consider what x could be, like if you factored it. So notice how if this is what sets your top of the derivative equal to 0, and then you factor, this could be 0 or this could be 0, so you kind of have two cases here. So we got, most of us got the 1, but we kind of got tripped up on the other one. Yeah?
How would x equal 0 count as a horizontal tangent?
So at this spot, you have a horizontal tangent. So on an x-axis, or on a graph, at this spot, you have a horizontal tangent. So if you were to take 0 and plug it in for the x's, okay, that's what I did here, all the x's would go away. If you solve, this is why you're able to use a calculator. If you solved this for y, you'd get the y value. So you'd have your point, you know your slope is 0, so you can write your equation of a tangent line. If you only considered y equals 2 and you tested that, you would have got like a no solution type deal. But this other case did lead you to a horizontal tangent line. Anything else? We sure? All right, you guys can keep those. Okay, I can tell you worked hard on them. Just a reminder that the other kind of criteria for this packet was that we're going to be having a pop quiz at some point. Okay, remember that was listed as one of the 7 things on the front. So you're not going to know when it is, okay, but it's just going to be 2 questions, very similar to the ones that were in here, okay, and you will not be able to use a calculator. So if you use the calculator on this, maybe go back and try to see if you can get the answers without one. All right? All right, in the meantime, we're going to wrap up this section on Rolle's theorem and the mean value theorem. So we just have 2 questions to go over, so it's going to be fairly short and simple. But I just want to go over visuals again for us to understand what these 2 theorems are telling us. So you don't have to write this down, okay? I just want you to pay attention, take a look at it, think about it. What if, let's see, we'll do a regular parabola, maybe that way. Both theorems from yesterday kind of involve the same criteria. We have a closed interval, we are differentiable, but there's one difference between Rolle's theorem and the mean value theorem. Can we remember or determine that difference? They're basically the same thing, except one is a little bit more specific, I guess, than the other one. Yeah, Anush?
For Rolle's theorem, the 2 endpoints need to be at the same height.
Okay, so for Rolle's, we have endpoints same height. Okay, for the mean value theorem, okay, mean meaning average. Okay, you're used to those synonyms. Average value, slope between 2 points, they don't have to be. Okay, so they don't have to be. So one of the things that we did yesterday, at least for the mean value theorem, is maybe we plotted some endpoints, okay, that had different heights, and we connected those with a secant line. And what the mean value theorem tells us is, since this graph is continuous and differentiable between those endpoints, we are able to drag this secant line either up or down, either direction, and it would eventually become a tangent line, specifically somewhere between the endpoints. So if I took this secant line and dragged it, keeping it parallel, notice how it would eventually become a tangent line right there. So this is kind of that special spot guaranteed by the mean value theorem. What I could do is change this up a bit, okay, make it the same graph. I have closed circles on the endpoints. If I connect those with a secant line, I get that. And if I drag it, notice how it becomes eventually a tangent line. Okay, so they're the same concept. It's just for Rolle's theorem, your secant line is horizontal, and that's what's going to lead you eventually to a critical point. But for a mean value theorem, your secant line is angled, and that's eventually going to lead you to some other tangent spot on the graph. So they're the same concept. It's just Rolle's is level, whereas mean value theorem is diagonal. Can we see the difference between the 2 from yesterday? Okay, so for Rolle's theorem, if we're finding a critical point, the derivative equals 0. For the mean value theorem, though, the derivative equals what? The slope of this line, okay, derivative, is the same as, yeah? Average rate of change, AROC. Okay, we enjoyed that from yesterday. And that is the slope between 2 points, okay, aka the slope of this secant line, okay? So I know we're not going to do any more Rolle's today because we exhausted that yesterday, bless you, but we have 2 more to go over today from the mean value theorem. Do we have a calculator? Yes. We may or may not need one, we'll see. All right. Let's take a look at the first one. explain why you cannot apply the mean value theorem for this function on this interval. So they're basically telling you that one of the criteria for the mean value theorem is not met. We want to figure out which one it is. Okay, so what are the conditions for the mean value theorem? Can we list them? What stipulations must we have? Yeah.
Continuous on the closed interval.
Continuous on a closed. Okay, yeah. Differentiable on the open. Okay. Rolls has the third kicker, which was the endpoints are the same, but we don't need that for mean value theorem. So one of these two is failing. Okay, so it's either not continuous here or it's not differentiable in here. So let's see what we can do. Do we know perhaps what the graph of a 2/3 power looks like? Maybe not. Okay, maybe we'll graph it just to see. All right, so x to the 2/3 minus 2. I'm going to change my window to our interval because we're only concerned with that little piece. And maybe I'll make the y's -5 to 5. All right, now we can manipulate the window to manipulate kind of what this shape looks like, but for this first piece or criteria, okay, for continuity, do we have any holes, jumps, or asymptotes? Definitely not, okay? Maybe since this wasn't even a fraction to begin with, we can rule out any of those possibilities because we know some things can go wrong for fractions. So we know we're continuous on the closed interval. That means something's going on with being able to find a derivative, okay, or take a derivative within this interval. Does there seem to be something interesting going on in this graph that we might want to pay attention to? Maybe. Okay, so maybe that's a sharp point right there. Okay, it might be hard to tell based off the calculator. Again, you might have to play with the window a little bit to actually see it, but this might be a sharp point. Let's go ahead and verify that using some calculus. So if we test the derivative, okay, just to see if it doesn't work somewhere, if we take a derivative, we'll have 2/3 x to the -1/3. If we clean it up, negative power can move to the bottom. So is there a number that would not work for this derivative? AKA it would be not differentiable at that spot. 0. X cannot equal 0. Is 0 within the interval? Yeah. Definitely. Okay, so we just confirmed, not graphically, but at least by hand, that this point on the graph must be a sharp point. So we'll say MVT fails because f of x is not differentiable at x equals 0. If you want to say there's a sharp point or a cusp, remember that's a synonym you could use, that would work as well. All right, so this is telling us that we're not guaranteed to have that special spot where the tangent line and the secant line have the same slope. There could be a special spot. We're just not guaranteed that there is one. So we're not really going to go any further with that, trying to search for something maybe when it's not even there. So if we're not guaranteed that it's there, we're just going to kind of let it go. You could search, but we're not going to go that far into it. Let's try the next one. Find the equation of a tangent line. Can we do that? Let's see, find the equation of a tangent line to this graph on the interval at the point which is guaranteed by the mean value theorem. What do we need to know to write the equation of a tangent line? A point and a slope. So we know we're going to have to plug in a point into the original function and the derivative. Now what's a little bit different with this question is usually up to this point they've told us what point to use, but it looks like they're asking us to find that point. Okay, it says at the point which is guaranteed by the mean value theorem. So we have to do a little bit of calculating first before we can even try to figure out the equation of this tangent line. So if they're telling us it's guaranteed by the mean value theorem, we automatically know that this function is continuous and differentiable within this interval. Okay? They might be just saying open parentheses there for the fact that they don't want us to include the endpoints for this special point. But since they're saying it's guaranteed, we know that we have brackets there for the graph itself. There are some closed circles there. So let's see. The mean value theorem says that the derivative, aka instantaneous rate of change, is equal to the average rate of change at some point. Okay, so let's see if we can figure this out. Instantaneous rate of change is derivative. Can we find the derivative of that function? 2 plus cosine x. So the derivative has to equal the average rate of change, the slope between 2 points. How do you think we can calculate that? Can we figure out the 2 points that they're giving us? Yeah?
Plugging in the endpoints and finding y value.
There we go. Plugging in the endpoints and we need y values. So the 0 and the pi are like your x values. So we can put those on the bottom. Okay, we need change in y's over change in x's. So we'll go ahead and put 0 and pi on the bottom. It doesn't matter how you subtract them. Remember, we need y2 minus y1 over x2 minus x1. So let's see. If I put 0 in the bottom first, that means I have to plug in 0 into the function and put that answer first up top. So if I plug in 0, 2 times 0 is 0, plus sine of 0, which is 0, and then plus 1 would be 1. And then we're going to have to subtract what we get when we plug in pi. So we're going to have 2 pi plus sine of pi. We're on that left-hand side. 0, and then plus 1. So 2 pi plus 0 plus 1. We're going to have 2 pi plus 1. Now be careful, because in your slope formula, y2 minus y1, you are subtracting both of these values together. So if 2 pi plus 1 is a value, you're subtracting the whole thing. Make sure you remember to put that in parentheses. So if we clean this up, 1 minus 2 pi and then minus 1, if we distribute the minus sign, looks like the 1's would cancel, and we're left with negative 2 pi up top. On the bottom, we'll have negative 2 pi, or negative pi. What's going to happen? What are we left with? Just 2, okay? So negatives and pi's cancel, so we're left with 2. So let's go ahead and find this special spot in between 0 and pi where the derivative is equal to this average rate of change, the secant line slope. So solving for x, if we subtract the 2, we'll get 0. All right, so on our unit circle, we got to think about where does cosine have a value of 0? If we start at 0, the cosine value is 1. If we move to pi over 2, that's 0. If we move to pi, it's negative 1. Move to 3 pi over 2, that's 0 again. Okay, we could keep going in a circle, right? However many times you want to revolve around. But I think this should be fine because we are anticipating something between 0 and pi. So between these options, looks like we'll just get pi over 2. Okay? So that's the special point that's guaranteed by the mean value theorem. This is the spot where the average rate of change becomes that instantaneous rate of change, that derivative tangent line graphically. So we're going to use this spot to help us find the equation of our tangent line. All right, I think we're good from here because we can figure out point and slope and write that out. So let's see, for our point, we'll plug in pi over 2. 2 times pi over 2 is pi, plus sine of pi over 2, sine at the very top. 1, okay, and then plus 1 on the end. So our point value is pi plus 2. Now we got to plug in pi over 2 into the derivative, and we already wrote that out to help us with our calculation. So 2 plus, we need cosine of pi over 2, 0. So we're left with 2. All right, so we know our point, we know our slope. We'll go ahead and write our equation. Y minus the point, make sure you subtract the whole thing, equals the slope times x minus pi over 2. We're doing okay? All right, at the very bottom, just so we have it, let's go ahead and write down the difference between Rolle's and the mean value theorem. Okay, so Rolle's, the instantaneous rate of change equals something, and then for the mean value theorem, the instantaneous rate of change equals something different. Instantaneous rate of change means derivative. What's the difference between the two? Yeah.
Rolls equals 0.
Yep.
And then the other one equals the
Average rate of change. Okay, AROC for short. Good. So they're very similar, like I said. It's just the difference between the two. Whether the endpoints are the same, meaning you have a horizontal line, aka slope of 0, or if the endpoints are not the same, you have a slanted line, so you have an average rate of change. Okay, they're very much connected, but they're slightly different. We doing okay? All right. With the 10-ish minutes that we have left, you can work on some homework problems. Don't forget the video assignment for tonight, and then comment on the Google form.